RDMA, as Brandon said, it was part of the original NVMe over Fabrics spec. I think it was called the binding specification for RDMA. And what RDMA is the remote version of DMA, or direct memory access. Direct memory access, just to set everybody at the same level, is an engine that's inside of CPUs that allows that CPU to move data from one part of its memory to another without the CPU actually doing it in code. So there's no software loop that's moving it a word at a time. Instead, you give this engine a pointer to the data you want to move, a pointer to where you want it to go, a counter, turn it on, it does it, no interaction with the CPU. So RDMA is the remote version of that. So in RDMA, there's capabilities in the NIC, sometimes called the RNIC for RDMA NIC, supporting NIC, that have this same type of engine. So you give the RNIC a pointer to the memory that you want to move across the network, and then you give it the counter, and from then on, the RNIC takes care of it, and there's no interaction with the CPU. It bypasses the traditional network stack, and it actually implements that network stack in that transport layer of the network stack in the adapter itself. So the TCP/IP stack basically takes care of making sure the data is delivered, if there's a problem with the delivery, retransmitting, et cetera, et cetera. It's basically like the mailman for the data you're moving across the network. And that all is now part of hardware on the NIC. So all hardware, very fast. That gives you, much higher bandwidth, very low latency, and more CPU power to use for your applications, which is what you usually buy your CPUs for. This isn't old technology. It's been around for many years. Actually, it was part of the InfiniBand technology that started way back in 2000 or before in the high-performance compute industry. And you can see over the years, InfiniBand became the dominant technology in the HPC space. And in fact, if you look at data, this is a little bit more newer data that actually shows the top 500 computers in the world. So these are all supercomputers, and you can see that InfiniBand dominates that space. So not just something new that we started and threw together with NVMe over Fabrics last year when the standard came out. So how this evolved into something you can run on Ethernet. The Ethernet version of RDMA is called Rocky, or RDMA over Converged Ethernet. And it's basically taking that InfiniBand protocol and applying it or moving it over to Ethernet. There are two different versions of it. Rocky v1 really isn't used much anymore because it's not routable. Rocky v2 is routable because it has a UDP and an IP layer. And basically, it's replaced Rocky. And when you hear the word, or Rocky v1, when you hear Rocky talked about, it means v2 for the most part now. Okay, one other thing on this slide that I forgot is that the transport layer, that hardware interface that's taking care of making sure the data gets to where you're sending it, is the same transport layer that was in InfiniBand, so tried and true. So it fits really, really well with NVMe over Fabrics, and that's because the NVMe, the underlying NVMe protocol, is very close to RDMA protocol. So in NVMe protocol, there's probably been many earlier talks on this, but basically you're taking that command from the NVMe stack, you're encapsulating it into the RDMA command, and you're sending it across the network. So basically the queuing mechanisms almost match up perfectly. So it comes out of the NVMe queue, goes into the RDMA queue, crosses the network, comes out of the incoming queue of the RDMA, goes into the submission queue, command control queue of the SSD, the remote SSD. And that is very low latency, and then the data gets moved, once the pointers are set up, the data gets moved with RDMA. So that's what makes NVMe over Fabrics so high performance, is there's hardly any overhead for the protocol. So if you want to, this is a look at that performance. This is data that Samsung presented at Red Hat Summit, and it shows latency, IOPS, and bandwidth for NVMe over Fabrics on Rocky. This is in a 24 SSD simulated all-flash array like Brandon was talking about earlier. And they did an interesting thing. So they took the test software, they ran it locally on the target, and they ran it remotely across the network. And then they compared it. So the local in blue, and the red is in remote, or the red is the remote. And they did another interesting thing is they ran it with 1 drive and then 24 drives. Because the setup was 25 gig on the initiators talking to dual 100 gigs on the target, you actually had a bandwidth constraint on those dual 100 gigs because 24 SSDs can overload 2 100 gig network ports. And so if you look at the 1 drive comparison in the chart below on latency, IOPS, and throughput, that's a much more representative of the capabilities of NVMe over Fabric, whereas the 25 or the 24 drive, some of the results or the differences come from the fact that there was a bottleneck. So there's lots of demonstrations. Hopefully the show floor opens tomorrow. This is a list of the demonstrations I'm aware of. If your company is demonstrating NVMe over Fabrics and you don't see your name up there, sorry about that. I just grabbed the ones off of memory that I knew about, and we can add you to the list for future presentations. Also, there's a list of announced shipping products. All of these are Rocky products, so these are products from companies that have announced or shown products at other shows. And then there's a list of reference designs. Pretty much all the SSD vendors have reference designs with Rocky and NVMe over Fabrics. So you go, if the show floor opens tomorrow, you'll be able to see most of these products there. The last thing I'm going to talk about, actually 2 more things. One is UNH. So UNH, for those of you that don't know, is an independent testing lab. They do a really cool thing. They take the students from the University of New Hampshire. The IOL employs those students, and they take the specifications, they go through them, they put logic analyzers on everything, and they make sure you're completely compliant with the specifications, and then they put you on a list as a compliant vendor. And they also do interoperability testing. So this test was done in May. It was multi-vendor test of NVMe over Fabrics. It was coupled with the NVMe by yearly testing they do for NVMe SSDs. And basically, we tested 2 vendors on both initiator and target, switched them around, and we were able to run at line rate. So one of the most important things about a new technology is you can buy it from multiple vendors and you can interchange those vendors. That's what makes a real technology. So the last thing I'm going to talk about is congestion management. So in order to get this high performance that I showed in earlier slides and we've all been talking about all day, you have to make sure that your network can handle the performance requirements. You can't, put this on 10 gig or have a 10 gig links or uplinks and expect all this to work. So what you have to do is pay really close attention to the congestion that can be created in the network. To get optimum performance. It'll work at less than optimum performance if you don't do this, but if you want the optimum performance, you have to pay attention to this. And one of the things that you can do is use a technology called PFC, or Priority Flow Control. That's an IEEE technology, and that was invented for fiber channel over Ethernet. And what it does is basically tell the network that, hey, or the network tells the adapter, hey, I've got too much data, you're overflowing me, quit sending me data until I tell you to start again. Another option is to use IETF, Explicit Congestion Management, or ECN. And basically what that does is, instead of saying stop, it just says, hey, I'm filling up, slow down. And it's a little bit more than that, and I'll show you about that in the next couple of slides. So for the IEEE pause frame, this is a typical example of when this comes into play. You've got too much data coming into one side, too little going out the other, and the switch starts to fill up at a certain threshold setting. It tells the sender, hey, quit sending data until I can drain out the data going to the end node. Priority version of that, or priority flow control, allows you to have multiple levels of this so that you can make sure that any high priority data can always get around a bottleneck. Explicit congestion management, or ECN, does it a little bit differently. Like I said, it tells you to slow down, but it also can go across multiple switches. With priority flow control, it's working just between a switch and a node. With ECN, it can work across a multi-switch network, and it's even better from the perspective that when congestion is detected on any switch, it sets a bit in the packet that triggered that congestion, and that packet then a message is echoed back from the destination to the source of this overload, and that tells that overloading source to back off, slow down, and then there's an algorithm that allows it to come back and speed up over time. And if it keeps congesting, it keeps getting told to slow down. So these are two very powerful methods to ensure that your network can handle the high performance and get the results you want to see with NVMe over fabrics. And that's my part.